Hi students, I want to talk about our first lesson here in AP Calculus. This lesson is going to talk about instantaneous rate of change. And you should be familiar with the phrase rate of change if you think about the slope. We talk about rise over run when we learn about linear functions in Algebra 1, and then we use that all the time. Even in geometry, we talk about the slopes of lines when they're parallel, the slopes of lines when they're perpendicular. We talk about it a lot. The interesting thing about calculus is that we're moving into thinking about slope in two different ways. We're talking about the instantaneous rate of change, and then we're also talking about the slope of a line that's not linear, which is a different topic. It's not in this first lesson, so we'll leave it aside, but just you could kind of ponder that for a moment. How would you find the slope of a line if it's changing, like a logarithmic function or even an exponential function? But we'll come back to that in the future. As far as instantaneous rate of change, think about, for example, like we just had the Olympics, right? And let's say that it's a particular race, like swimming. When the swimmer first jumps off into the water and they make that dive, they're gonna go at a certain speed, but they're not going to maintain the exact speed the whole time, right? At certain times, they'll be speeding up, and then as they get close to the wall, they'll have a moment of slowing down, they'll make their flip turn and start back and pick up speed again. And so there's different speeds at different moments, but we can take their average speed by doing the same formula that we've always done for slope. You know, we can take 2 points and say, well, this was their time and where they were at this moment, and then here's the time and where they were at that moment, and we can do the regular slope formula. But what if I want to know what was the speed of that swimmer at exactly 23 seconds into the race, or when were they going their highest speed? That you know, throwing a baseball, there were baseball in the Olympics. Let's say you're throwing a ball and you say, okay, this baseball traveled at 96 miles per hour. Well, was it going 96 miles per hour the entire time? No, because it left the pitcher's hand and the speed would have changed at different moments until either someone hit the ball or the catcher caught it. So what if we wanted to know what was the actual maximum speed? At what moment was it going its highest speed? Well, in calculus, we learn how we can get as close to possible as knowing exactly what that might be. And so this first lesson is about instantaneous rate of change. So let's look at that. Okay, let's discuss this concept of instantaneous rate of change. We'll use some various examples to see some application of it. So reading this first paragraph, as students of life and algebra, you have studied many rates of change for different situations. How fast we drive, how our savings grow over time, the rate that the world population changes, our growth rate every year, unemployment rates, and so much more. In each of these studies, we can express one variable in terms of another. That is, as a function, y equals f of x. Thinking about more common times with COVID, we have lots of rates of change. You know, what's the rate of positive tests and negative tests? What's the rate of death? What's the rate of severe reaction? The vaccines, all kind of stuff. So rates of change happen everywhere. We're going to look specifically at a term from physics called velocity. And we're going to consider an object that travels in a straight line. The average velocity over some given time interval can be defined as the ratio of the change in position, so here we have change in position, to the elapsed time period, which, think about it, elapsed time would be like the change in time. And do note these two keywords, displacement or net change is another way to say change in position. I want to introduce a symbol to you in case you're not familiar. This triangle, we say delta. It's a Greek letter delta, and it means change. It's used in a lot of different careers, concepts, different subject areas, all kind of things. Delta is the symbol for change. So for average velocity, we could write the ratio as change in position over change in time. And if we were abbreviating that, we would say delta D because of distance over delta T for time. So this is the way we abbreviate it. You're going to see a lot of delta use going forward if you haven't seen it in any earlier classes. So when we think of velocity, we usually mean instantaneous velocity, which indicates the speed and direction of some object at a particular moment. So in velocity and physics, they're usually talking about, like, they use vectors and things like that because it tells you the speed that something is going and the direction, okay?
it could be faster at any given moment or slower than the average velocity. Because if you think about the example I mentioned in the intro about a swimmer, when they dive into the pool and then they get to the center of the pool, they're kind of going as fast as they can swim generally. And then as they come near the wall, they're going to have to slow down to prepare to turn around to the other direction. So at different times, their speed could be faster or slower than their average, because the average is going to take into account the whole thing. And then, it's just like your grades. You could have grades, you have to have grades that are higher than your average and grades that are lower than your average, because your average is in the middle, right? So that makes sense. Here's a question. Can you explain why we can't define instantaneous velocity as a ratio? So the question is, why can't we define it as a ratio? Well, first we could just think about it. If you are doing only an instant, there's no change in time in an instant. It's an exact moment. So how would we have the denominator? Where would our denominator come from if there's no change in time? We wouldn't have t minus t1, So the other thing is, if we did have, let's say that we just used the same time, then what would happen is division by a 0. So since we can't have division by 0, this wouldn't work, because so here's our answer. The time interval is 0. Division by 0 is undefined. We can't do that. So the next question is, how can you estimate an instantaneous velocity? So thinking about the idea that we're taking the average, and we could say, well, what if I want the average between 0 seconds and 10 seconds? That's a pretty big gap. What if I brought it down from 0 seconds to 5 seconds? Or I could go even closer, 0 seconds to 1 second. What if I went really, really close and it was 0 and 0.1, or 0 and 0.001? I can make this a smaller and smaller time interval, and that is going to give me a closer and closer approximation to an exact instant. So here we have it, by making the time interval very small. And here's a summary to put this idea into a thought. We'll generalize it. Average velocity over a very small time interval, average velocity over a very small time interval is very close to instantaneous velocity. Getting very close, we have to accept, is it good enough? So let's look at example number 1. If you climb to the top of the Tower of Pisa and drop a coin to the ground, estimate the instantaneous velocity at t equals 0.7 seconds. Use Galileo's formula, s of t equals 16 times t squared, to compute the average velocity in feet per second over the time intervals listed in the table. So first of all, I don't know why it's s of t, because it is talking about a rate in change of the distance, like how far the coin has fallen from beginning until it hits the ground. So it's more like a distance. I don't know what the S represents, but it's fine. We can still do the problem. So let me point out to you a formula. We need to know the change in distance over the change in time. So we've got, oh, that's the highlighter, my bad. We've got delta D over delta T. The delta T is easy. Remember, these are our time intervals. So this would be like time 1 and time 2. So over here, I'm going to do T2 minus T1. This is my change in time. On top, it's a little more confusing. You have to actually calculate. That's what the formula is for. So we're actually going to have on top S of T2 minus S of T1. So we're going to have to work out using this formula on top. For the first example, it would be 16 times 0.71 squared minus 16 times 0.7 squared, all over 0.71 minus 0.7. And then we would get this answer, 22.56. What I would first suggest is that you enter this into your calculator, even though you already have the answer. Enter it in your calculator and make sure you get the same answer. Then you have confirmed that you're entering it correctly. And then you can go ahead and do these next 4. Pause the video here, work it out yourself, and then check your answers. Because entering the information in the calculator and getting it correct is one of the key things to making sure that you're getting through AP Calculus. You don't want a small little error here and there to add up and be the reason that you don't get a 5 or a 4 on the AP exam. But also, let me tell you that you want to leave enough decimal places after the decimal. Leave enough places. The general rule for AP exam is 3 places after the decimal. I'm going to write that down here at the bottom, and you can check your answers here on this row. Okay, so after you've checked your answers, hopefully that all worked out correctly, and here's the 2 notes I made at the bottom. Have 3 digits after the decimal, and do not round until the end. As you're working things out, you've got to keep from rounding until the very last step, because we all know that it can change your answer quite significantly. So looking here at these answers, if you got a different answer than what I have, it could be because you rounded too early. Now I've got to erase because we wrote in our space here. If you need this information, you can go back in the video. But the question is, what is your estimate for the instantaneous rate of change? So what I'm going to say is that the coin, let me just autofill it so that you guys don't have to wait for me to write it out. Okay, the coin is falling at a rate of about 22.400 feet per second at t equals 0.7 seconds. We say about because remember the question is, what is your estimate? We're just seeing how close we can get, and they added a whole bunch of zeros to get really close. Okay, so this is our estimate. One more note, in the AP exam and in math in general, you should know this. It is very important that we use our units. Include your units, okay? So let's look at the next page. The study of rate of change is fundamental to the study of calculus. Yes, rate of change is kind of one of the keys. In our first example, we allowed the time interval to shrink to 0. So you can say that the average velocity converges, meaning it's like moving towards the instantaneous velocity. It converges to the instantaneous velocity. Or that the instantaneous velocity is the limit of the average velocity. This is a key word. This is like one of the top 5 words in calculus. So the instantaneous velocity is the limit of the average velocity. That might sound strange, but think about what it means. And as we're working through, it's going to become more and more clear over the next several lessons. So here's a graphical representation of velocity. The average speed, they abbreviate that AROC, which means average rate of change, is defined by the total distance traveled d divided by the elapsed time period t. Graphically, the average speed is the slope of the secant line. Interesting because secant, especially the secant line, not talking about secant like the trig function, but the secant like when you learned about circles. The secant is the line that intersects a curve at 2 points. So it kind of goes through the circle and touches it twice. Okay, so the average speed is the slope of the secant line. So if I were to draw here on the computer a secant line, it would look like this. I don't know why I said I drew it on the computer, I guess because I'm writing digitally. But here's my secant line in purple. It's connecting those 2 points, A and B. Analytically, average speed, AROC, equals delta D over delta T. These two things work together. Sketch the secant line through A and B. We just did that. Estimate the average velocity. So basically, we're going to use a slope formula. Okay, that's the general thing that's going to happen here. So this first point A is 1, 3, and the second point B is 4, 4. So we're going to do the change in X and the change in Y. Remember, X goes on bottom. I just said it first because X comes first. So we have the Y's 4 minus 3, and on the X's 4 minus 1. What's 4 minus 3? 1. What's 4 minus 1? 3. We've estimated the average velocity. Okay? Keep in mind, this is just the average velocity between A and B. It's not meaning on this entire graph. It could be the same if we chose 2 different points. It could be different. Okay? So we're just saying between points A and B, the average rate of change or the average speed is 1/3. So let's go to the next set. Instantaneous speed, IROC, is the speed at a specific instant in time where t equals t sub 0 is the limit of the average rates of change. So think about that. T sub 0 is the instantaneous, because remember back up here they used the word limit. Instantaneous velocity is the limit of the average velocity. So T sub 0 is representing the instantaneous rate of change. It's the limit of the average rate of changes. And that still sounds weird because we haven't really learned about limits. But basically think of it as really what the word limit means in English. Like, this is the limit, you can't go any further. So for just right now, momentarily, until we learn more about limit, think of it as what it means in English. It's just saying it's got to get closer and closer to that number. That's where it's going toward. So graphically, the instantaneous speed is the slope of the tangent line. Again, this is talking about when you think about a circle. A tangent is a line that touches the curve at one point, exactly one point, and it's like it just barely touches. Let me draw it on here. Now, I'll tell you, the tangent line is harder to draw than any other because it's supposed to be touching in only this one exact point and then continuing on without touching the rest of the curve. So this would be the slope of the tangent is how we would find the instantaneous speed, because think about that. It's like as close as you can get to being in the exact point, okay? So looking at the tangent line, we need to do the rate of change. But one thing that's good to note right here, we need calculus to determine this actual answer. So we can't technically do it yet. That's what we're going to be learning. This is just examples, remember, to get us thinking about what does this look like. But if we've sketched the tangent line now, can we estimate the instantaneous velocity at x equals c? Well, notice right up here, there's a point right here where it looks like it's pretty much touching the tangent line as well. And it's a nice clear point. So it's the point 5, 6. And we already had this point where that's a 2, not a 3. We already had the original point that we were drawing the tangent line to. So we can just do the regular old standard slope, 6 minus 4 over 5 minus 2, and we're going to get 2/3. So that's what we're going to make as our estimate, right? So this is our first two examples, or first example. I guess it was really two because we had the Leaning Tower of Pisa thing. But let's keep going. This one I think will be a little bit more clear in how we did the first one using the formula again. This whole example was just to help you see. Notice the difference between the secant line and the tangent line. The secant line is 2 points. It doesn't really matter where they are. You can connect any 2 points and take the slope of the line. This tangent line is barely touching exactly the curve. And so that's basically saying, what is the slope at this one and only point? Okay? So keep that in mind as we go forward into future lessons. Let's look at example number 2. Have you ever taken a spin class at the gym? A spin class is like cycling and you have a coach trying to get you to, it's like a stationary bike. Then you know that after the class is over, your rapid heart rate decreases as time passes. Let h of t represent your heart rate. Write an expression for the rate of change of your heart rate over the period from t equals 0 seconds to t equals 90 seconds after you have stopped exercising. So all this is asking us to do is write an expression for it. And we've got a time frame of 0 and 90 seconds. So t sub 1 is 0. And t sub 2 is 90. We know that much. And what's our heart rate? Well, we don't know, but we know that it's h of t. So what do we need here? H of 0 and h of 90. Since we're only writing an expression, we don't actually need to work this out. So we can just say, what is the change in h over the change in time? Well, it would be h of 90 minus h of 0. H of 90, remember, is my heart rate at 90 seconds. H of 0 is my heart rate at 0 seconds. So h of 90 minus h of 0 over 90 minus 0. And that's it. This one's actually done, except we didn't write our units. Heart rate is measured in beats, and our time is in seconds. So it's beats per second. Second, not seconds. So there's that one. Let's go to the next page. Now, I know this video is getting a bit long, so feel free to pause, get up, move around, and come back to it. Unfortunately, that is the nature of the beast when we're doing something completely new. Okay, let's look at this example about the roller coaster. A hypercoaster is a special circuit roller coaster with a height measuring greater than 200 feet. That's interesting. If a new hypercoaster is under design to have its largest drop, have its largest drop on the circuit modeled by the equation below, where d of t is measured in feet and time t is measured in seconds. So this is the formula to have its, say it again, d of t is measured in feet. The largest drop, meaning like, think of like steepest part of the roller coaster, is modeled at this equation. So this equation is going to measure it for you, like what is the drop at this time? What's the drop in distance? Like how much distance is changing at a specific time. Find the average speed or velocity of the hypercoaster from 2 seconds to 8 seconds. So this is where we're actually going to go back to that formula that we were using. In this case, it's d of t. So we're going to have d of t for the 8 seconds. So that's going to be d of 8 seconds minus the d of 2 seconds over 8 minus 2. This is my delta. I wrote it as an A. Delta d over delta t. This is what it's going to be. Delta d over delta t. D of 8 minus d of 2 over 8 minus 2. Again, this is going to be a situation where you're going to need to put it in your calculator. You can do this entire formula and get the answer. So the first one is 671.36. If you haven't done it yet, pause the video and check your work. The second one, the d of t, is going to be 290.54. And that is all going to be divided by 6 because 8 minus 2 is 6. So you do your subtraction on the top, divide by 6, and you're going to get 63.47 feet per second. Imagine that. That's like dropping 5 floors of a building. That would be taller than the building at Logos, and that you dropped all the way to the ground in 1 second. That's crazy. So that's how we do that. And I just realized I can leave this as an equal. It's not an estimate because it's an exact. So we had a time interval and we did the formula. So look at the next one. What is the average speed velocity of the hypercoaster from 4 seconds to 6 seconds? This is the same thing. We just have 4 and 6. So we're looking at average rate of speed, which you can write this instead of delta d over delta t if you want. And we're going to do d of 6 minus d of 4 over 6 minus 4. This one I'm just going to have automatically appear and you can check your answer, but pause to make sure you're doing it right. Okay, so I added in the answer here on letter B, but also notice the 2 green lines. The average rate of speed of change, average rate of change on the interval where time is between 2 and 8. So 2 is less than t is less than or equal to 8 seconds is about 63.47 feet per second. Same thing on the next one. We have the AORC on the interval from 4 to 6 seconds. It's about 48.51 feet per second. So it is necessary to write these things out. As I mentioned before, they do expect that on the AP exam. So we need to get used to it because as you just noticed, I forgot to add it in there. So let's keep going if you checked your answer. And notice this was an equal sign and then it changes. We went from using an equal sign to using the approximate because we started to round. As soon as we round, we got to use our little squiggly, which is like approximately. So coming to the next one, estimate the instantaneous speed velocity of the hypercoaster at exactly 5 seconds. Notice here we're doing the same thing like we did on the first page where we're getting more and more decimals. Again, pause the video and do it and then check your work. Notice that it's this same formula right here, okay? So that's what you're going to be using to answer these 3 fill in the box. So here are the answers. Go ahead and check your numbers. Notice they're all rounded to 4 decimal places. So check your answers. Notice we put feet per second every time. And then we need to also write out our explanation. Okay, so here's our description. The instantaneous speed of the hypercoaster at 5 seconds is about 46.647 feet per second. Again, final answer having 3 decimal places. So go back up and look. Notice what happened. Here, we had a pretty broad interval from 8 to 2 seconds. That was 63.47. That's pretty fast. Then when we went from 6 to 4 seconds, that made it a little bit smaller interval. We dropped all the way down to 48, and now look what happened. When we got closer, the 46.647 is pretty close to 48.5, but it's like 2 feet difference. Talking about only 1 second, that's pretty significant. So explain the meaning of the instantaneous speed or velocity in the context of the question at t equals 5 seconds. So let me make that appear for us again. Here we go. The rate of change in the drop of the hypercoaster at t equals 5 seconds is about 46.647 feet per second. So that's pretty close here, except we said the instantaneous speed in the example in red, or in the answer in red. And so looking at D, the rate of change in the drop of the hypercoaster. So we added, what does it actually mean? What's happening? The coaster is dropping at this speed. Okay? Okay, one more page, airport departures. On this one, it's very similar to what we were doing. You're going to use that same formula. So I'm going to give you more of the information more quickly. And then there's only one other thing that's going to be different, is that we're going to make a sketch. So let's read this. The traffic pattern of departing flights at Orlando International Airport on a fall afternoon can be modeled by the function v, defined by v of t equals 92 minus 15 sine of t over 3. I need to not underline that incorrectly. Where v of t is measured in vehicles and t is measured in minutes. Let me use the highlighter and so I can stop doing that. T is measured in minutes, v of t is measured in vehicles. So we're looking at, as the vehicles come, they can also look at how many people are on departing flights. It's like a ratio, it's comparison. The traffic pattern of departing flights can be modeled by the number of cars in the minutes. So let's look at it. Find v of t for t equals 18. You guys know how to do this. You're just going to do v of 18. So pause, get the answer, and check your... Okay, so we got about 96 vehicles. Hopefully you got the same answer. So looking at part B, make a sketch of the graph of time versus number of vehicles. Be sure your graph has a scale. Okay, so we're going to draw a sample graph over here. You are more than welcome to look on Desmos or look on your graphing calculator. Honestly, it's better if you use your graphing calculator. If you're not sure how to do that, if this is new to you, turn it on, and at the very top you'll see the y equals, and you can type in this function 92 minus 15 sine parentheses t over 3, and then close your parentheses, and then you'll be able to go to the graph. It won't be on your screen because we've got really big numbers, 92 minus 15. And what do we know about the sine function from pre-cal? We know that it's like a wave like this. So if 92 is on the graph, we're going to be around 92. So you might set your window. If you push the window button, it says X minimum and X maximum. What do you want to see? I'm going to put mine on like 75 and 110. How did I get that? I just went a little bigger than 92 and a little smaller. My Y, oh, sorry, and that's going to be my Y, not my X. My X, I'm still just going to leave it as the negative 10 and the 10. But my Y, I'm going to change to 110 and 75. And then I'm going to graph it and be able to see this lovely little curve. And actually, you could change your X to be 0 to 30. That would actually give you the perfect window to view the time frame that it's telling you that it wants you to draw. And so you just need to draw the picture that looks like this, what you see on your calculator. So here it is on the screen. So here's my graph neatly labeled. You do need to say on one side, on the Y, vehicles, and on the bottom, minutes. And notice we plotted our 1 point that we know, v of t, v of 18. And the curve should look something like this. I didn't do a good job. This should actually be the same. So this should come down the same as this one does. Hopefully you did a better job than I did. Let's look at question C. What is the average rate of change of the vehicles as the departing flights over the time interval 15 to 20? So remember, this is the formula that we're going to use from before. The average rate of change. The AROC is going to equal the change in the distance, or in this case, the change in the number of vehicles. So we're using V, and in my head, I keep thinking D. This is V of 20 minus V of 15 divided by 20 minus 15. This is the formula that we're using. And so you can get your answer, but you're going to have to do some rounding, so you're going to want to use that it's an estimate. And so work this out and then check your answer. So we've worked it out. We got our subtraction here. If you actually wrote out your steps, you can see in case you got anything wrong. Here's our estimated answer, negative 3.9992 vehicles per minute. So how do we write that out in words? Let's explain it. Okay, so here we have in purple. On the interval from 15 to 20 minutes, the number of vehicles at the departing flights is decreasing at a rate of about 4 vehicles per minute. Okay? So this is what we have just explained. We looked at this interval from 15 to 20 minutes. That's a 5-minute range. Now, estimate the instantaneous rate of change of vehicles at t equals 18 by finding the average rates. So we're estimating by getting closer and closer to 18. So use your formula, the same formula for V of t up here, 92 minus 15 sine t of 3 is what you're going to use. But when I'm saying use your formula, I'm actually referring to this one. You're going to need both, because now we have 18 minutes, and these are the different time intervals that they have given us. So you need to find all 3 answers. So go ahead and pause. If you haven't been doing that at all, please remember that we have like 2 more questions to answer, this one and 1 more, and then you're going to do the practice by yourself. So if you haven't tried anything, you need to go ahead and do it on the calculator and make sure that you're typing it in correctly and that you can use the formula, because I'm not giving it to you clearly on this one. You need to set it up yourself. So here are the numbers. Notice that they're negatives, and they're all rounded to 3 decimal places, and we have the units, vehicles per minute. Now, let's write our description. Okay, the instantaneous rate of change at t equals 18 minutes is decreasing at a rate of about 4.8 vehicles per minute. So, coming down to one last question. Why can't the instantaneous rate of change of traffic in the departure lane with respect to time be calculated using the method in part D? When I read this question on this worksheet, I thought that it was kind of a weird question, because it didn't make sense to me why you would, like, I was trying to figure out, well, what are they getting at? You know, is it something complicated? Don't overthink it. Why can't the instantaneous rate of change of traffic, blah, blah, blah. Anytime that you see this part right here, that why can't the instantaneous rate of change be calculated? Notice that we can't calculate it, we just estimated it. Why can't we calculate it? The same thing we said back at the beginning of the video. Division by 0 would occur. You can't have division by 0. It's not allowed. So this isn't a super scientific way to say it or mathematical, but this is the bottom line. Division by 0 would occur, and that's not allowed. So that's why you can't do it. So what you're going to do now is go ahead and work through the examples and, the practice page, and then we'll come back together next time.